What were the major reasons for 16th century advances in European mathematics?
There are several reasons for advances in mathematics at the end of the Middle Ages. The major reason, of course, was the beginning of the Renaissance. A time when there was a renewed interest in learning. Another important event that pushed mathematics was the invention of printing, which made many mathematics books, along with useful mathematical tables, available to a wide audience. Still another advancement was the replacement of the clumsy Roman numeral system by Hindu-Arabic numerals. For more information about the Hindu-Arabic numerals, see Math Basics.
How did our present day become divided into hours, minutes, and seconds?
Divisions into hours, minutes, and seconds probably began with the Sumerians around 3000 BCE. They divided the day into 12 periods, and the periods into 30 sections. About 1000 years later, the Babylonian civilization, which was then in the same area as the Sumerians, broke the day into 24 hours. Europe around 20,000 years ago recorded days between successive new moons. Another hypothesis states that the measurement of time dates back some 10,000 years, which coincides with the development of agriculture, especially in terms of when to best plant crops. Still others point to timekeeping evidence dating back 5,000 to 6,000 years ago around the Middle East and North Africa. Whatever the true beginnings, most researchers agree that timekeeping is one of those subjects whose history will probably never be accurately known.
What are some familiar Arabic terms used in mathematics?
There are numerous Arabic terms we use today in our studies of mathematics. One of the most familiar is the term algebra, which came from the title of the book, Al-Jabr w al-Muqabala by Persian mathematician Muhammad ibn Musa al-Khwarizmi, 783 c. 850, also seen as al-Khwarizmi and al-Khwarizmi. He was the scholar who described the rules needed to do mathematical calculations in the Hindu-Arabic numeration system. The book, whose title is roughly translated as Transposition and Reduction, explains all about the basics of algebra. For more information, see algebra. Another Arabic derivation is algorithm, which stems from the Latinized version of Muhammad ibn Musa al-Khwarizmi's own name. Over time, his name evolved from al-Khwarizmi to al-Khwarizmi, then algoritmi, algorithmus, algorithm, and finally algorithm.
What is the definition of a clock?
A clock, from the Latin clicca, or bell, is an instrument we use for measuring time. There are actually two main qualities that define a clock. First, it must have a regular, constant, or repetitive action, or process, that will effectively mark off equal increments of time. For example, in the old days before our battery-driven, analog and digital clocks and watches, clocks included marking candles in even increments, or using a specific amount of sand in an hourglass to measure time. Second, there has to be a way to keep track of the time increments and easily display the results. This eventually led to the development of watches, large clocks such as Big Ben in London, England, and even the clocks that count down the new year. The most accurate clocks today are atomic clocks, which use an atomic frequency standard as the counter.
What was the House of Wisdom?
Around 786, the fifth caliph of the Abbasid dynasty began with Caliph Harun al-Rashid, a leader who encouraged learning, including the translation of many major Greek treatises into Arabic, such as Euclid's Elements. Al-Ma'mun, 786 to 833, the next caliph, was even more interested in scholarship, creating the House of Wisdom in Baghdad, one of several scientific centers in the Islamic Empire. Here, too, Greek works such as Galen's medical writings and Ptolemy's astronomical treatises were translated, not by language experts ignorant of mathematics, but by scientists and mathematicians such as Al-Kindi, 801 to 873. Muhammad ibn Musa al-Khwarizmi, see below, and the famous translator Hunan ibn Ishaq, 809 to 873.
What are the basic Roman numerals and how are they used?
There are only 7 basic Roman numerals, as seen in the following chart. Number Roman numeral 1 I5 V10 X50 L500 D1000 M. There are many rules, of course, to this method of writing numerals. For example, although the way to write a large number like 8000 would be M, this is very cumbersome. In order to work with such large numbers, one rule was to write a bar over a numeral, meaning to multiply by 1000. Thus, 8,000 would be 8 equal to our Hindu-Arabic number 8 with a bar over the entire Roman numeral.
What were some early measurements of weight?
Some of the early measurements of weight include the grain, pound, and ton. Ancient peoples used stones, seeds, and beans to measure weight. But grain, such as wheat or barley corn, was a favorite. In fact, the grain, abbreviated GR, is still one of the smallest units of weight used today. To compare, 1 pound equals 7,000 grains. The traditional pound as a unit of weight was used throughout the Roman Empire. But like many other measurements over time, the number of ounces in a pound seemed to shift and change. For example, the number of ounces in the Roman pound was 12. European merchants used 16 ounces to the pound. Eventually, 16 ounces in a pound became standard. For more about ounces, see below. Back in the 19th century, the Americans who did not like the British larger weights decided that a hundredweight would equal 100 pounds, the British hundredweight was 112. This meant a ton was equal to 20 hundredweight for the American ton, or the Americans' short ton was 2,000 pounds. While the British long ton of 20 hundredweight was equal to 2,240 pounds. There were, of course, debates, but not everyone disagreed with the American short ton. It became the favorite of British merchants, who called it a sundial. Eventually, the ton on the international market went metric. And today a metric ton is close to the original British long ton. It is equal to 1,000 kilograms, or approximately 2,204 pounds, and is officially called a ton. Although the international system, SI, CP 50, standard uses ton, the United States government recommends using the metric ton.
What were some early units used for calculating length?
The earliest length measurements reach back into ancient time, and it is a convoluted history. Some of the earliest measurements of length are the cubit, digit, inch, yard, mile, furlong, and pace. One of the earliest recorded length units is the cubit. It was invented by the Egyptians around 3000 BCE and was represented by the length of a man's arm from his elbow to his extended fingertips. Of course, not every person has the same body proportions, so a cubit could be off by a few inches. This was something the more precision-oriented Egyptians fixed by developing a standard royal cubit. This was maintained on a black granite rod accessible to all, enabling the citizenry to make their own measuring rods fit the royal standard. The Egyptian cubit was not the only one. By 1700 BCE the Babylonians had changed the measurement of a cubit, making it slightly longer. In our measurement standards today, the Egyptian cubit would be equal to 524 millimeters, 20.63 inches. And the Babylonian cubit, cubit 2, would be equal to 530 millimeters, 20.87 inches. The metric unit millimeters is used here, as it is an easier way to see the difference between these two cubits. As the name implies, a digit was measured by the width of a person's middle finger and was considered the smallest basic unit of length. The Egyptians divided the digit into other units. For example, 28 digits equaled a cubit, 4 digits equaled a palm, and 5 digits equaled a hand. They further divided 3 palms, or 12 digits, into a small span, 14 digits. Or a half cubit, into a large span, and 24 digits into a small cubit. To get smaller measurements than a digit, the Egyptians used fractions. Over time, the measurement of an inch was all over the measurement map. For example, 1 inch was once defined as the distance from the tip to the first joint on a man's finger. The ancient civilization of the Harappan in the Punjab used the Indus inch. Based on ruler markings found at excavation sites, it measured, in modern terms, about 1.32 inches, 3.35 centimeters, see below for more about the Harappan. The inch was defined as 1/36 of King Henry I of England's arm in the 11th century. And by the 14th century, King Edward II of England ruled that 1 inch equaled 3 grains of barley corn placed end to end lengthwise. See box on p46 for more about both kings. Longer measurements were often measured by such units as yards, furlongs, and miles in Europe. At first, the yard was the length of a man's belt, also called a girdle. The yard became more standard for a while, when it was determined to be the distance from King Henry I's nose to the thumb of his outstretched arm. The term mile is derived from the Roman mil passus, or 1,000 double steps, also called paces. The mile was determined by measuring 1,000 double steps, with each double step by a Roman soldier measuring 5 feet. Thus, 1,000 double steps equaled a mile, or 5,000 feet, 1,524 meters. The current measurement of feet in a mile came in 1595, when, during the reign of England's Queen Elizabeth I, it was agreed that 5,280 feet, 1,609 meters, would equal 1 mile. This was mainly chosen because of the popularity of the furlong. 8 furlongs equaled 5,280 feet. Finally, the pace was once attached to the Roman mile, see above. Today, a pace is a general measurement, defined as the length of one average step by an adult human, or about 2.5 to 3 feet, 0.76 to 0.19 meters.
What was the driving force behind the development of accurate clocks?
The true driving force behind accurate clocks began around the 16th century in relation to finding longitudinal measurement. As countries began to explore the world, an accurate way of telling a ship's position became a critical problem. With one time standard around the world, and clocks to tell those times, longitude, and thus position, could be determined. This would not only mean an increase in exploration but also wealth for the sponsoring country.
Who was Omar Khayyam?
Omar Khayyam, 1048 to 1131. Who was actually known as Al-Khayyami, was a Persian mathematician, poet, and astronomer. He wrote the treatise on demonstration of problems of algebra, a book that contains a complete classification of cubic equations with geometric solutions. all of which are found by means of intersecting conic sections. He solved the general cubic equation hundreds of years before Niccolò Tartaglia in the 16th century. But his work only had positive roots. Because it was completely geometrical, see elsewhere in this chapter for more about Tartaglia. He also calculated the length of the year to be 365.24219858156 days, a remarkably accurate result for his time, and proved that algebra was definitely related to geometry.
What did the Chinese add to the study of mathematics?
Despite the attention the Greeks have received concerning the development of mathematics, the Chinese were by no means uninterested in it. About the year 200 BCE, the Chinese developed place value notation. And 100 years later they began to use negative numbers.
What is the most famous Chinese mathematics book?
The Zhuzang Suanchu, or 9 chapters on the mathematical art, is the most famous mathematical book to come out of ancient China. This book dominated mathematical development for more than 1,500 years. With contributions by numerous Chinese scholars such as Su Yu, c. 160 c. 227, though his contributions were lost. It contains 246 problems, meant to provide methods to solve everyday questions concerning engineering, trade, taxation, and surveying.
How was, and is, 1 second defined?
A second was once defined as 1/86,400 of a mean solar day. By 1956 this definition was changed by the International Bureau of Weights and Measures to 1/31,556,925.9747 of the length of the tropical year 1900. But like most measurements, the second definition changed again in 1964, when it was assigned to be the equivalent of 9,192,631. 770 cycles of radiation associated with a particular change in state of a cesium-133 atom. Interestingly enough, by 1983 the second became the definer of the meter. Scientists defined a meter as 1/299,792,458 the distance light travels in 1 second. This was done because the distance light travels in 1 second was more accurate than the former definition of the standard meter.
How are mathematics and the study of time connected?
Mathematics is definitely tied to time. There has long been a need in human civilizations to record many sequences of events, especially those in nature that affected people. For example, the changing of the seasons was important to know, as it influenced the planting and growing of crops, when rivers would flood, and even when weather would change from monsoon rains and harsh droughts to potential blizzards. The first such timekeepers counted the changing days and years by the movement of stars, the sun, and the moon across the sky, all of which are activities that included simple mathematical calculations.
What are the methods for converting temperatures between the various scales?
He following lists ways to convert from one temperature scale to another using, of course, simple mathematics. Fahrenheit to Celsius, C degree equals, F degree 32/1.8, also seen as 5/9, F degree 32, Celsius to Fahrenheit, F degree equals C degree x 1.8, plus 32, also seen as 9/5, C degree, plus 32 Fahrenheit to Kelvin, K degree equals F degree 32/1.8 plus 273.15 Kelvin to Fahrenheit. F degree equals, K degree 273.15, x 1.8 plus 32 Celsius to Kelvin, K degree equals C degree plus 273.15 Kelvin to Celsius, C degree equals K degree 273.
Why is Omar Khayyam so famous?
Omar Khayyam is not as well known for his contributions to math as he is for being immortalized by Edward Fitzgerald, the 19th century English poet who translated Khayyam's own 600 short, 4-line poems in the Rubaiyat. However, Fitzgerald's translations were not exact, and most scholars agree that Khayyam did not write the line "a jug of wine, a loaf of bread, and thou." Those words were actually conceived by Fitzgerald. Interestingly enough, versions of the forms and verses used in the Rubaiyat existed in Persian literature long before Khayyam, and only about 120 verses can be attributed to him directly.
What were the ancient definitions of a foot?
Not all feet, or the foot, are created equal. The term foot in measurement has had a long history, with many stories claiming the origin of the first foot status. In fact, it seems as if the foot has ranged in size over the years from 9.84 to 13.39 inches, 25 to 34 centimeters, depending on the time period and/or civilization. For example, the ancient Harappan civilization of the Punjab, from around 2500 to 1700 BCE, used a measurement interpreted by many to represent a foot, a very large foot, at about 13.2 inches, 33.5 centimeters, see above for more about the Harappan. Around 1700 BCE, the Babylonians put their foot forward. A Babylonian foot was 2 othirds of a Babylonian cubit. There are even records from Mesopotamia and Egypt showing yet another measurement system that included a foot of 11.0238 inches, 300 millimeters. This was also known as the Egyptian foot, and it was standard in Egypt from pre-dynastic times to the first millennium BCE. The Greek foot came close to today's foot, measuring about 12.1 inches. 30.8 centimeters, a Roman foot measured in at 11.7 inches, 29.6 centimeters. The list goes on, depending on the country and time period.
Upon what system were ancient measurements based?
Initially, people used different measurement systems and methods depending on where they lived. Most towns had their own measurement system, which was based on the materials the residents had at hand. This made it difficult to trade from region to region. Measurements eventually became based on familiar and common items. But that did not mean they were accurate. For example, length measurements were often based on parts of the human body, such as the length of a foot or width of the middle finger. Longer lengths would be determined by strides or distances between outstretched arms, because people were of different heights and body types. This meant the measurements changed depending on who did the measuring. Still, they were close enough for the needs at the time. Even longer lengths were based on familiar sites. For example, an acre was the amount of land that 2 oxen could plow in a day.
Where did the pound, and its abbreviation, lb, originate?
The origin of the word pound comes from libra pondo, or pound of weight. The common abbreviation for pound, lb, originated from letters in the Latin word libra, or balanced scales.
What were some of the contributions by the Arab world to mathematics?
From about 700 to 1300, the Islamic culture was one of the most advanced civilizations in the West. The contributions of Arabic scholars to mathematics were helped not only by their contact with so many other cultures, mainly from India and China, but also because of the Islamic Empire's unifying, dominant Arabic language. Using knowledge from the Greeks, Arabian mathematics grew. The introduction of Indian numerals, often called Arabic numerals, also helped with mathematical calculations.
Who developed the idea of a foot in measurement?
Here is quite a mystery about who first developed the foot as a measurement unit. One story, which most scholars believe is a legend, is that a foot was the length of Charlemagne's, 742 to 814, foot. Charlemagne, also known as Charles the Great, was king of the Franks and emperor of the Holy Roman Empire. Standing at 6 feet 4 inches tall, he probably had a really big foot. Still another story involves England's King Henry I. 1068 to 1135, in which the length of an arm became important. Henry I ruled that the standard foot would be 1/3 of his 36-inch long arm. This thus became the origin of our standardized unit of 12 inches to a foot. The inch being 1/36 of a yard. According to the Oxford English Dictionary. The first confirmed usage of the word foot as a unit of measurement also occurred during the reign of Henry I. In honor of his arm, he ordered that an iron ulna, the ulna being the longer, inner bone in the forearm, be made. This iron stick represented the master's standard yard for the entire kingdom. But around 1324, in response to his subjects' cries for an even more standard measurement, England's King Edward II, 1284 to 1327, changed things again. Recognizing the iron ulna was not universally available, he declared that 3 barley corns, round and dry, make an inch, and that 12 inches, or 36 barley corns, would equal 1 foot. It's interesting to note that even shoe sizes were tied to King Edward II and barley corns. He declared that the difference between one shoe size to the next was the length of 1 barley corn.
How was the standard foot determined?
Whatever the true story, the foot we are familiar with today is equal to 12 inches, 30.48 centimeters. The true standardization of the foot came late in the 19th century. After the United States and Britain signed the Treaty of the Meter. In this treaty, the foot was officially defined in terms of the new metric standards being adopted overseas. In the United States, the Metric Act of 1866 further defined the foot as equal to exactly 1200/3937 meter, or about 30.48006096 centimeters. This unit of measurement is still used for geodetic surveying purposes in the United States, and is called the survey foot. By 1959, the United States National Bureau of Standards redefined the foot to equal exactly 30.48 centimeters, or about 0.999998 survey feet. This definition was also adopted in Britain by the Weights and Measures Act of 1963, thus, a foot, or 30.48 centimeters, is also called an international foot.
What is the historical significance of the barley corn in measurement?
The barley corn, just a grain of barley, definitely had a significant historical role in determining the length of an inch and the English foot. For more about the inch and foot, see below. In addition, in traditional English law, the various pound weights all referred to multiples of the grain. A single barleycorn's weight equaled a grain, and multiples of a grain were important in weight measurement. Thus, some researchers believe the lowly barleycorn was actually at the origin of both weight and distance units in the English system.
What is the origin of Roman numerals?
Because the history of Roman numerals is not well documented, their origin is highly debated. It is thought that the numerals were developed around 500 BCE, partially from primitive Greek alphabet symbols that were not incorporated into Latin. The actual reasons for the 7 standard symbols are also argued. Some researchers believe the symbol for 1, I, was derived from one digit on the hand, the symbol for 5, V, may have developed because the outstretched hand held vertically forms a V from the space between the thumb and first finger. The symbol for 10, X, may have been 2 V's joined at the points. Or it may have had to do with the way people or merchants used their hands to count in a way that resembled an X. All the reasons offered so far have merely been educated guesses. However the symbols were developed, they were used with efficiency and with remarkable aptitude by the Romans. Unlike the ancient Greeks, the Romans weren't truly interested in pure math, such as abstract geometry. Instead, they concentrated on applied math, using mathematics and their Roman numerals for more practical purposes, such as building roads, temples, bridges, and aqueducts, for keeping merchant accounts, and for managing supplies for their armies. Centuries after the Roman Empire fell, various cultures continued to use Roman numerals. Even today, the symbols are still in existence. They are used on certain timepieces, in formal documents, and for listing dates in the form of years. For example, just watch the end credits of your favorite movie or television program, and you will often see the movie's copyright date represented with Roman numerals.
What is the difference between the various pounds and ounces?
The story behind the ounce is long and convoluted because historically people have been dissatisfied with the unit. For example, in medieval times English merchants were not happy with the troy pound, as it was less than the commercial pound in most of Europe. In response, the merchants developed an even larger pound, which was called the libra mercatoria, or mercantile pound. But by 1300 the complaints about the mercantile pound grew, because 15 troy ounces, or 7,200 grains, were easily divided by 15 and its divisors, but this was not as convenient as dividing by 12 troy ounces. Soon, another type of pound was born in English commerce, the 16-ounce avoirdupois. roughly translated from the Old French as goods of weight. Modeled on a common Italian pound unit of the late 13th century. The avoirdupois pound weighed exactly 7,000 grains, which is easily divided for use in sales and trade. But because it was difficult to convert between the troy and avoirdupois units. The avoirdupois ounce is 7,000/16 or 437.5 grains, and 1 grain equals 1/7,000 avoirdupois pound. Or 1/5,760 troy or apothecaries pound. The troy ounce is 5,760/12,480 grains. Or 31.1035 grams in metric. The standard soon shifted to using mostly the avoirdupois unit. The avoirdupois is currently used in the United States and Britain. It is equal to 1/16 of a pound, or 28.3495 grams, in metric. The avoirdupois ounce is further divided into 16 drams, or dram. The troy ounce hasn't been totally forgotten, though. Today, it is used mainly as units for precious metals and drugs, where it is often called the apothecary's ounce. With its subdivisions of the scruple, or 20 grains, and the dram, or 60 grains. In turn, the avoirdupois hour ounce for short is used for almost everything else.
How is temperature measured?
Temperature is measured using a thermometer, thermo meaning heat and meter meaning to measure. The inventor of the thermometer was probably Galileo Galilei, 1564 to 1642. Who used a device called the thermoscope to measure hot and cold. Temperatures are determined using various scales, the most popular being Celsius, Fahrenheit, and Kelvin. Invented by Swedish astronomer, mathematician, and physicist Anders Celsius. 1701 to 1744, in 1742, Celsius used to be called the centigrade scale. It can be capitalized or not. Centigrade means divided into 100 degrees. He used 0 degrees Celsius to mark the freezing point of water. The point where water boils was marked as 100 degrees Celsius. Because of its ease of use, mainly because it is based on an even 100 degrees. It is the scale most used by scientists. It is also the scale most associated with the metric system. Fahrenheit is the scale invented by Polish-born German physicist Daniel Gabriel Fahrenheit. 1686 to 1736, in 1724. His thermometer contained mercury in a long, thin tube, which responded to changes in temperatures. He arbitrarily decided that the difference between water freezing and boiling 32 degrees Fahrenheit and 212 degrees Fahrenheit, respectively would be 180 degrees. The Kelvin scale was invented in 1848 by Lord Kelvin, 1824 to 1907. Who was also known as Sir William Thomson, Baron Kelvin of Largs. His scale starts at 0 degrees Kelvin, a point that is also known as absolute zero. The temperature at which all molecular activity ceases and the coldest temperature possible. His idea was that there was no limit to how hot things can get, but there was a limit to how cold. Kelvin's absolute zero is equal to minus 273.15 degrees Celsius, or minus 459.67 degrees Fahrenheit. So far, scientists believe nothing in the universe can get that cold.
What is the connection between calendars and math?
A calendar is essentially a numbering system that represents a systematic way of organizing days into weeks, months, years, and millennia, especially in terms of a human lifespan. It was the necessity to count, keep track of, and organize days, months, and so on that gave rise to calendars. All of which also entails the knowledge of mathematics to make such calculations.
Why were early Greek calendars such a mess?
And like the Mesopotamian cultures, the early Greeks paid less attention to astronomy and more to cosmology. They were interested in studying where the Earth and other cosmic bodies stand in relation to the universe. Because of this, their astronomical observations were not accurate, creating confusing calendars. This also led to a major conundrum: almost every Greek city kept time differently. In fact, during the Greek and Hellenistic times, most dates were given in terms of the Olympiads. This only created another timekeeping problem: if something happened during the 10th Olympiad, it meant the event occurred within a 4-year span. Such notation creates headaches for historians, who end up making educated guesses as to the actual dates of Greek events. Important people's deaths and births, and other significant historical occurrences.
What are some standard measurement units and their definitions?
For a helpful list of standard measurement units and systems for converting them to other types of units, see Appendix 1 in the back of this book.
How does a sundial work?
The sundial tracks the apparent movement of the sun across the sky. It does this by casting a shadow on the surface of a usually circular dial marked by hour and minute lines. The gnomon, or the shadow casting angular object on the dial, becomes the axis about which the sun appears to rotate. To work correctly, it must point to the north celestial pole, near the star Polaris, also called the North Star. Thus, the gnomon's angle is determined by the latitude of the user. For example, New York City is located at about 40.5 degrees north latitude. So a gnomon on a sundial in that city would be at a 40.5 degree angle on a sundial. The sharper the shadow line, the greater the accuracy. In addition, larger sundials are more accurate, because the hour line can be divided into smaller units of time. But the sundial can't be too large. Eventually, diffraction of the sunlight around the gnomon causes the shadow to soften, making the time more difficult to read.
Who first introduced Arabic notation and the concept of zero to Europe?
Italian mathematician Leonardo of Pisa, c. 1170 c. 1250, who was also known as Fibonacci, or son of Bonaccii, although some historians say there is no evidence that he or his contemporaries ever used that name, brought the idea of Arabic notation and the concept of zero to Europe. His book Liber Abaci, the Book of the Abacus, not only introduced zero but also the arithmetic and algebra he had learned in Arab countries. Another book, Liber Quadratorum, the Book of the Square, was the first major European advance in number theory in 1,000 years. He is also responsible for presenting the Fibonacci sequence. For more information about Fibonacci and the Fibonacci sequence, see Math Basics.
What culture took the first steps toward timekeeping?
Around 5,000 years ago, the Sumerians in the Tigris-Euphrates Valley, today's Iraq, appear to have had a calendar, but it is unknown if they truly had a timekeeping device. The Sumerians divided the year into months of 30 days. The day was then divided into 12 periods, each corresponding to 2 of our modern hours, and the periods into 30 parts, each corresponding to 4 of our minutes. Overall, many researchers agree that the Egyptians were the first serious timekeepers. Around 3500 BCE, they erected obelisks, tall, four-sided monuments, placing them in specific places in order to cast shadows as the sun moved overhead. This thus created a large, crude form of a sundial. This sundial time was broken into 2 parts, before noon and after noon. Eventually, more divisions would be added, breaking down the time units even more into hours. Based on the length of the obelisk's shadows, the huge sundials could also be used to determine the longest and shortest days of the year.
What was one of the first devices used to measure time?
One of the first devices smaller than the obelisks mentioned above to measure time was a crude sundial. By about 1500 BCE, the true, small sundial, or shadow clock, was developed in Egypt. It was divided into 10 parts, with 2 twilight hours marked. But it could only tell time for half a day, afternoon. The sundial had to be turned 180 degrees to measure the afternoon hours. More refinements of measuring time occurred later. in order to correct for the sun's changing path over the sky throughout the year. The no-manor object that creates the shadow on the sundial had to be set at the correct angle, what we call latitude. Eventually, the sundial was perfected. Multiple designs were used. For example, shortly before 27 BCE, the Roman architect Marcus Vitruvius Polios, c. 90 to 20 BCE, De Architectura described 13 different designs of sundials.
Is measurement tied to mathematics?
Yes, measurement is definitely tied to mathematics. In particular, the first steps toward mathematics was using units and eventually numbers to describe physical quantities. There had to be a way to add and subtract the quantities. And most of those crude calculations were based on fundamental mathematics. For example, in order to trade horses for gold, merchants had to agree on how much a certain amount of gold, usually as weight, was worth, then translate that weight measurement into their barter system. In other words, X amount of gold would equal Y amount of horses.
What was the first civilization to use a decimal system of weights and measures?
Between 2500 and 1700 BCE, the Harappa, or Harappan civilization of the Punjab, now a province in Pakistan, developed the earliest known decimal system of weights and measures. For more about decimals, see Math Basics. The proof was first found in the modern Punjab region, where cubical, some say hexahedral, weights in graduated sizes were uncovered at Harappa excavations. Archaeologists believe that these weights were used as a standard Harappan weight system, represented by the ratio 1:2:4:8:1632:64. The small weights have been found in many of the regional settlements and were probably used for trade and or collecting taxes. The smallest weight is 0.8375 grams, 0.00185 pounds, or as measured by the Harappa, 0.8525, the most common weight is approximately 13.4 grams, 0.02954 pounds, or in Harappa, 13.64, the 16th ratio. Some larger weights represent a decimal increase, or 100 times the most common weight, the 16th ratio. Other weights correspond to ratios of 0.05, 0.1, 0.2, 0.5, 1, 2, 5, 10, 20, 50, 100, 200, and 500. There is also evidence that the Harappan civilization had some of the most advanced length measurements of the time. For example, a bronze rod found at an excavation was marked in units of precisely 0.367 inch, 0.93 centimeter. Such a measuring stick was perfect to plan roads, to construct drains for the cities, and even to build homes. An ivory scale found at Lethal, once occupied by the Harappan civilization, is the smallest division ever recorded on any measuring stick yet found from the Bronze Age. With each division approximately 0.06709 inch, 0.1704 centimeter, apart.
What is some of the earliest evidence of keeping time?
No one agrees which culture, first invented timekeeping. Some historians and archaeologists believe that marks on sticks and bones made by ice age hunters in with each hour composed of 60 minutes, and each minute having 60 seconds. It is unknown why the Babylonians chose to divide by 60, also called a base number. Theories range from connections to the number of days in a year, weights and measurements, and even that the base 60 system was somehow easier for them to use. Whatever the explanation, their methods proved to be important to us centuries later. We still use 60 as the basis of our timekeeping system: hours, minutes, seconds. And in our definitions of circular measurements, degrees, minutes, seconds. For more information about the Sumerian counting system, see History of Mathematics.
When were the first calendars invented?
Although the first crude types of calendars may have appeared some 30,000 years ago, they were based on the movements of the moon and indicated as marks on bones. The Egyptians are given credit for having the first true calendars. Scientists believe that around 4500 BCE the Egyptians needed such a tool to keep track of the Nile River's flooding. From about 4236 BCE, the beginning of the year was chosen as the heliacal rising, when a star is finally seen after being blocked by the sun's light, of the star Sirius, the brightest star in the sky located in the constellation of Canis Major. This occurred, and still occurs, in July, with the Nile flooding shortly after that, which made it a perfect starting point for the Egyptian calendar. The Egyptians divided the calendar into 365 days, but it was not the only calendar they used. There was also one used for planting and growing crops that was dependent on the lunar month.
When were the first calendars invented?
Although the first crude types of calendars may have appeared some 30,000 years ago, they were based on the movements of the moon and indicated as marks on bones. The Egyptians are given credit for having the first true calendars. Scientists believe that around 4500 BCE the Egyptians needed such a tool to keep track of the Nile River's flooding. From about 4236 BCE, the beginning of the year was chosen as the heliacal rising, when a star is finally seen after being blocked by the sun's light, of the star Sirius. The brightest star in the sky located in the constellation of Canis Major. This occurred, and still occurs, in July, with the Nile flooding shortly after that, which made it a perfect starting point for the Egyptian calendar. The Egyptians divided the calendar into 365 days, but it was not the only calendar they used. There was also one used for planting and growing crops that was dependent on the lunar month.
What is a lunar-based calendar?
A lunar calendar is a calendar based on the orbit of our moon. The new moon, when you can't see the moon because it is aligned with the sun, is usually the starting point of a lunar calendar. From there, the various phases seen from Earth include crescent, first quarter, and gibbous. These phases after a new moon are also labeled waxing, such as waxing crescent. When the entire face is seen, it is called a full moon. From there, the phases are seen in reverse, and are labeled waning, such as waning crescent. Overall, the entire moon cycle takes about 29.530589 days. This cycle was used by many early cultures as a natural calendar.
What is a lunar-based calendar?
A lunar calendar is a calendar based on the orbit of our moon. The new moon, when you can't see the moon because it is aligned with the sun, is usually the starting point of a lunar calendar. From there, the various phases seen from Earth include crescent, first quarter, and gibbous. These phases after a new moon are also labeled waxing, such as waxing crescent. When the entire face is seen, it is called a full moon. From there, the phases are seen in reverse, and are labeled waning, such as waning crescent. Overall, the entire moon cycle takes about 29.530589 days. This cycle was used by many early cultures as a natural calendar.
What was the problem with the lunar-based calendars?
Nothing is perfect, especially a lunar month. The biggest drawback with using a lunar calendar is the fractional number of days, which makes a lunar calendar quickly go out of sync with the actual phases of the moon. The first month would be off by about a half a day, the next month a day, the next month a day and a half, and so on. One way to help solve the problem was to alternate 30 and 29-day months. But this, too, eventually made the calendars go out of sync. To compensate, certain cultures added intercalations or subtracted extracalations days from their calendar. For example, for more than 1,000 years, the Muslims' lunar calendar has had an intercalation of 11 extra days over a period of 30 years, with each year being 12 lunar months. This calendar is only out of sync about one day every 2,500 years. To see this, mathematically speaking, the average length of a month over a 30-year period is figured out with the following equation. 29.5 x 360 plus 11/360 equals 29.530556 days, in which 11 is the number of intercalated days. 360 is the number of months in a 30-year cycle, 12 months x 30 years. And 29.5 is the average number of days in the calendar month, or 29 plus 30/2.
What was the problem with the lunar-based calendars?
Nothing is perfect, especially a lunar month. The biggest drawback with using a lunar calendar is the fractional number of days, which makes a lunar calendar quickly go out of sync with the actual phases of the moon. The first month would be off by about a half a day, the next month a day, the next month a day and a half, and so on. One way to help solve the problem was to alternate 30 and 29-day months. But this, too, eventually made the calendars go out of sync. To compensate, certain cultures added intercalations or subtracted extracalations days from their calendar. For example, for more than 1,000 years, the Muslims' lunar calendar has had an intercalation of 11 extra days over a period of 30 years, with each year being 12 lunar months. This calendar is only out of sync about one day every 2,500 years. To see this, mathematically speaking, the average length of a month over a 30-year period is figured out with the following equation. 29.5 x 360 plus 11/360 equals 29.530556 days, in which 11 is the number of intercalated days. 360 is the number of months in a 30-year cycle, 12 months x 30 years. And 29.5 is the average number of days in the calendar month, or 29 plus 30/2.
What is a solar-based calendar?
A solar-based calendar is one based on the apparent movement of the Sun across the sky as we orbit around our star.
What is a solar-based calendar?
A solar-based calendar is one based on the apparent movement of the Sun across the sky as we orbit around our star.
How did some ancient cultures refine their calendars?
There were many different ways that various ancient cultures refined their calendars. And all of them entailed some type of mathematical calculation. One way to measure the length of a year was by using a gnomon, or a structure that casts a shadow. For more about gnomons and sundials, see p. 57. This was based on the apparent motion of the sun across the sky, with the shadow not only used to tell daily time but also to determine the summer solstice, when the shadow created by the gnomon would be at its shortest at noon. By measuring 2 successive summer solstices and counting the days in between. Various ancient cultures such as the Egyptians developed a more detailed calendar and, as a bonus, determined the exact times of the solstice. Around 135 BCE, Greek astronomer and mathematician Hipparchus of Rhodes, c. 170–c. 125 BCE, decided to compare his estimate of the vernal spring in the northern hemisphere, occurring in March, equinox with that made by another astronomer about 150 years earlier. By averaging the number of days, he estimated that a year was equal to 365.24667 days. A number only off by about 6 minutes and 16 seconds.
How did some ancient cultures refine their calendars?
There were many different ways that various ancient cultures refined their calendars. And all of them entailed some type of mathematical calculation. One way to measure the length of a year was by using a gnomon, or a structure that casts a shadow. For more about gnomons and sundials, see p. 57. This was based on the apparent motion of the sun across the sky, with the shadow not only used to tell daily time but also to determine the summer solstice, when the shadow created by the gnomon would be at its shortest at noon. By measuring 2 successive summer solstices and counting the days in between. Various ancient cultures such as the Egyptians developed a more detailed calendar and, as a bonus, determined the exact times of the solstice. Around 135 BCE, Greek astronomer and mathematician Hipparchus of Rhodes, c. 170–c. 125 BCE, decided to compare his estimate of the vernal spring in the northern hemisphere, occurring in March, equinox with that made by another astronomer about 150 years earlier. By averaging the number of days, he estimated that a year was equal to 365.24667 days. A number only off by about 6 minutes and 16 seconds.
What was the Roman calendar?
The first Roman calendar, according to legend, appeared when Rome was founded around 750 BCE. When it actually started is still up for discussion. But the calendar was based on the complexity of the solar-lunar cycles. At first, the calendar had 10 months, starting in March. January and February were added as the calendar was modified. Politics entered into the determination of this calendar, too, with certain officials deciding to add days whenever they desired, and even what to name certain months.
What was the Roman calendar?
The first Roman calendar, according to legend, appeared when Rome was founded around 750 BCE. When it actually started is still up for discussion. But the calendar was based on the complexity of the solar-lunar cycles. At first, the calendar had 10 months, starting in March. January and February were added as the calendar was modified. Politics entered into the determination of this calendar, too, with certain officials deciding to add days whenever they desired, and even what to name certain months.
What was the Julian calendar?
By the time of Julius Caesar, 100 to 44 BCE, Roman calendar keeping was a mess. Caesar decided to reform the Roman calendar. Asking help from astronomer and mathematician Sosigenes of Alexandria, lived c. 1 BCE, not to be confused with Sosigenes the Peripatetic c. 2nd century, an Egyptian philosopher. The year 46 BCE would consequently have 445 days, a time appropriately called the Year of Confusion. Sosigenes began the reformed year on January 1, 45 BCE, a year with 365 days, and proposed an additional day for every fourth year in February, leap day. The alternate months of the year, January, March, May, July, September, November, had 31 days, the other months would have 30 days. In the Julian calendar, there was only one rule: every year divisible by 4 was a leap year. The vain heir to Caesar, Augustus Caesar, 63 BCE 14 CE, aka Gaius Octavius, Octavian, Julius Caesar Octavianus, and Caesar Augustus, would change the Julian calendar in several ways. Not only did he name the month of August after himself, but he would change the number of days in many months to their present usage, adding more confusion to the calendar. The Julian calendar would govern Caesar's part of the world until 1582. Not that the Julian year was perfect. A year's 364.25 days was too long by 11 minutes 12 seconds. Although the difference between today's measurement of the year and the Julian year was not great, it adds up to 7.8 days over 1,000 years. But as with many decrees and mandates, Caesar, Sosigenes, and Octavian left it up to future generations to fix the problem.
What was the Julian calendar?
By the time of Julius Caesar, 100 to 44 BCE, Roman calendar keeping was a mess. Caesar decided to reform the Roman calendar. Asking help from astronomer and mathematician Sosigenes of Alexandria, lived c. 1 BCE, not to be confused with Sosigenes the Peripatetic c. 2nd century, an Egyptian philosopher. The year 46 BCE would consequently have 445 days, a time appropriately called the Year of Confusion. Sosigenes began the reformed year on January 1, 45 BCE, a year with 365 days. And proposed an additional day for every fourth year in February, leap day. The alternate months of the year, January, March, May, July, September, November, had 31 days, the other months would have 30 days. In the Julian calendar, there was only one rule: every year divisible by 4 was a leap year. The vain heir to Caesar, Augustus Caesar, 63 BCE 14 CE, aka Gaius Octavius, Octavian. Julius Caesar Octavianus, and Caesar Augustus, would change the Julian calendar in several ways. Not only did he name the month of August after himself, but he would change the number of days in many months to their present usage, adding more confusion to the calendar. The Julian calendar would govern Caesar's part of the world until 1582. Not that the Julian year was perfect. A year's 364.25 days was too long by 11 minutes 12 seconds. Although the difference between today's measurement of the year and the Julian year was not great, it adds up to 7.8 days over 1,000 years. But as with many decrees and mandates, Caesar, Sosigenes, and Octavian left it up to future generations to fix the problem.